Section 7.3 is volume, the shell method. Now the shell method is a different way to find the volume of the solid of revolution. And what the shell method does is that it takes a strip of the solid that is parallel to the axis of rotation so that when you rotate it, it forms cylindrical shells. So it takes a region, this yellow region right here, and let's say that we're rotating this guy here about the y-axis. It takes a strip from each one of these and makes it into a cylindrical shell. Think of it as a Russian doll. So something inside of something else inside of something else in order to make the volume of that solid. That's basically what the cylindrical shells or the shell method is. But let's look at a picture of it from a video so that you have a better understanding of what it looks like. Basically, if you have some curve, let's say we have this curve and we're rotating it around the y-axis, what the shell method does is it takes one region and it sweeps out this cylindrical shell so that you have the volume of the solid made by a bunch of cylindrical shells. And again, the more shells you put in there, the more accurate your volume is. So you kind of get an idea from here, all these shells being swept out and then used to find the volume of this region. What we're going to do is we're going to use again the shell method to find the volume of the solid. Since we're looking at those cylindrical shells, we're basically using surface area, so 2 pi r, times your thickness, which is going to end up being your height. So to find the volume, we're going to be using volume equals 2 pi times radius, which the book calls p of y, and the height, which the book calls h of y. If you're looking at this picture here, basically your radius is still going to be perpendicular to your axis of rotation. So you're going to go out some units for a radius, and your height is parallel to your axis of rotation and is inside that yellow region. In this case, it would be right there. That would be your height. Let's take a look at the two general formulas for the shell method, and then we'll look at problems involving the shell method. Just like last time, we're going to have revolving around a horizontal and a vertical axis of revolution. And as we said before, the radius is still always going to be perpendicular to that axis of revolution. The difference though now is that if you have a horizontal axis of revolution, for the shell method, you integrate with respect to y, not x. So our formula is going to be 2 pi times the integral from a to b of your radius, which is going to be something of y, and then a height, which is also going to be something of y. Let's say that we're taking this and we're revolving it around our x-axis, and we're looking at, let's say, this region right here. Our radius is going to always be, again, perpendicular to our axis of rotation. So we're going to call this guy here our radius. And our height is the distance inside of our yellow region. Now, just to let you know, if the axis of rotation is the x-axis, your radius is always just y. Now let's look at a vertical axis of rotation. So if we have a vertical axis of rotation, for the shell method, we're going to integrate with respect to x. So if we have this region right here, and let's say we're taking this region right here, and we're rotating this region right here around the y-axis, our radius again is always going to be perpendicular to that axis of rotation. So here's our radius. And our height is going to be parallel to that axis of rotation, so that would be our height. Formula is always going to be 2 pi times the integral from a to b of radius times height. Now, if that axis of revolution equals the y-axis, your radius is always just x. If the axis of revolution is not the x-axis or the y-axis, then the radius is going to be the distance between curves, and we're going to look at that when we get there in terms of what the radius would be. So let's look at the next few examples, and we're asked to use the shell method to write and evaluate the definite integral that represents the volume of the solid generated by revolving the plane region about the given line. Example 1 says that we're bounded by y equals 4x minus x squared and y equals 0, and we're going to do this about the y-axis. Well, the y-axis is vertical. Since it's vertical, we know that we need to integrate with respect to x. Let's go ahead and graph this so that we can find the limits of integration, the radius, and the height. Because remember, for that shell method, your formula is always going to be volume equals 2 pi times the integral from a to b of your radius times your height, and it's going to be dx if you have a vertical axis of revolution and dy if you have a horizontal axis of revolution. If we graph this, the first one that we have here, y equals 4x minus x squared, that we know is a parabola that opens down. So we're going to do two things. We're going to find its vertex by completing the square, and we're going to find the x-intercepts so that it's easier for us to graph this. The x-intercept first, setting y equal to 0, 0 equals 4x minus x squared. Factoring out an x, and I have 4 minus x left. Setting both of those equal to 0, and you get x is equal to 0 and x is equal to 4. So I'll cross the x-axis at 0 and 4. In order to complete the square, I first need to write it in descending order. So y equals negative x squared plus 4x. Factor out the negative, x squared minus 4x. Now remember to add in that blank. But remember, we're not really adding inside the parentheses because of the negative in front. So the opposite of subtraction would be addition, and I would write that on the outside. Then here the variable is x, and then I write down half of that term. Half of the coefficient of the x term is negative 2. If I square the number I just wrote down, negative 2 squared is 4, and that's the number that I write in those blanks. Now I'm going to move this over with the y, and I get y minus 4 is equal to the negative of x minus 2 squared. So the vertex of this parabola is going to be the opposite of the number with x is 2. The opposite of the number with y is 4. Going ahead and graphing this now. Our vertex again is 2, 4, and we cross the x-axis at 0 and at 4. It's a parabola that opens down, so we just finish it off. The other thing we're bounded by is y equals 0. Well, that's easy to draw. That's just the x-axis. So the region that we're looking at is this region right here. And we're going to take this region and we're going to revolve it around the y-axis. What we need to do now is determine if we can see the limits of integration in x. Well, yes, we can. We are integrating from x equals 0 to x equals 4 because those are our bounds. Now we need to find the radius and the height. Well, the radius is always going to be perpendicular to your axis of rotation. So in this case, the radius is going to be the distance from there to there. That's your radius. Well, that radius is just an x movement because to get from the y-axis over to where I just drew that dot, I have to move x units. So the radius here is just going to be equal to x. Recall I said on the page before, if you're rotating about the y-axis, your radius is always just going to be x. So I know my radius. My radius is going to be x. Now I need my height. Well, the height is going to be the distance inside of that yellow area. Well, the distance inside of this yellow area is green. Well, green here is 4x minus x squared all the way down to blue. Well, blue is 0. So your height here is 4x minus x squared. Go ahead and write that into our volume formula over here, 4x minus x squared. Now we'll have to distribute before we integrate. If I distribute the x, I have 4x squared minus x cubed dx. Integrating, we have 4x cubed over 3 minus x to the 4th over 4, and this gets evaluated from 0 to 4. Plugging in those limits of integration, we have 4 times 4 cubed over 3 minus 4 to the 4th over 4, and if I plug in zeros, both of those terms will just be 0. Grabbing a calculator to get the final answer here, if I plug in 4 times 4 to the 3rd divided by 3, and then I subtract from it 4 to the 4th over 4, I end up with 64 over 3. So I get b equals 2 pi times 64 over 3. If I multiply that number by 2, I end up with 128 over 3. So my volume here is going to be 128 pi over 3. Let's look at example 2. Example 2 is y equal 2x, y equal x over 2, x equal 1. So that's my region, and I'm going to rotate that region around the y-axis. The y-axis is vertical. Since it's vertical, I know I need to integrate with respect to x. Coming over here and graphing all of these. Y equal 2x is just a line. It has a y-intercept of 0 and a slope of 2. So I draw that line, y-intercept of 0, slope of 2. And there we go. That is y equal 2x. Y equal x over 2 is also a line. It has a slope of a half and a y-intercept of 0. So y-intercept of 0, up 1 over 2. There's y equal x over 2. The last thing that I have to draw is x equal 1. Well, x equal 1 is just going to be a vertical line at 1. So the region that we're looking at is trapped between all three of those, and it's that region right there. So I know that I have a vertical axis of rotation, which means I need to integrate with respect to x. So the question is, can you see the limits of integration from this picture? Yes, absolutely. You are bounded by x equals 0, and then this x equal 1. So your limits of integration there are going to be from 0 to 1. Now you need to find your radius and your height. Remember, you're rotating this about the y-axis. So the radius is going to be the distance from the axis of revolution to somewhere in the yellow. And so this here, this radius, if we think about it, is just an x movement, so my radius is going to be x. Recall, if your axis of revolution is the y-axis, then your radius is always just going to be x. Your height is going to be the distance inside of this yellow region. Well, that distance for my height is going to be the blue curve, which is 2x, minus the pink curve, which was x over 2. Well, that's really just 2x minus a half x, and that's going to be 3 over 2x. So my height is 3/2 x. Coming back over here and finishing that off in the formula. So we have b equals 2 pi times the integral from 0 to 1 of x times 3/2 x. Well, 3/2 is a constant multiplier, so I can pull that out. And if I multiply 3/2 by 2, I end up with just 3. So my volume is equal to 3 pi times the integral from 0 to 1, and then x times x is just your x squared. Integrating this, and you get x cubed over 3, and this gets evaluated from 0 to 1. Plugging in those limits of integration, and this we won't use a calculator for because it's so simple. It's just going to be 1/3 minus 0, so your volume here is just going to be pi.